Hi, my name is Basem Barakat, and I'm here with my colleague, Evelyn Ding, and to present the hyperparameter optimization for the MLPerf training with SigOpt. This work is uh, also has contribution from Joshua Mora and many other individuals and engineers from the Habana Lab. I would like to provide an overview about the work we're presenting here in this slide. The focus of our work is to reduce the MLPerf workload training time. The optimization applied to two workloads of the MLPerf training is the ResNet 50 and BERT. I included a link to the MLPerf training for those who would like to look at it. However, this link is for the version 1.0. We have submission done for version 1.1, and these result is not public yet. So for that reason, I will not presenting the result as in absolute numbers. We will show a relative performance. Once that result became publicly, we could do that, and probably this is by the end of this month. The method is applied to ResNet 50 and BERT, but it's really general and could be applied to any other workload. But here we will presenting the ResNet 50 because the method is identical. So I would like to emphasize and make sure everybody understands that many factors contribute to optimizing at scale workloads, execution time. We will be focusing and discussing the hyperparameter optimization contribution to that performance of that workload. And also, I would like to mention, we're starting from a known value. So these workloads are known, they ran several times. So we will start at the known values, and then we will go ahead and apply our methods. In addition, we don't have infinite computer resources, although our group has a lot of resources, but they're shared with other groups and other they have other objectives. For the hyperparameter optimizations, our goal is to achieve the work with the least number of nodes using the least number of times. So the shortest number of times. And we'll be comparing the optimization work done manually and against the one done with SigOpt when we applied SigOpt. So I'm providing references here to what we're optimizing. So these workloads, both ResNet and BERT, we're not optimizing the models themselves. We're optimizing the cost functions. And namely, that's LARS and LAM. So these are the reference papers which describe the cost functions used and so to provide more details for you. Obviously, you could think about it, we're optimizing the optimizers. So the algorithms are highlighted in these papers. I put a shot of them here. It's basically we're optimizing the scheduler of the weight decay. So the optimizer has a schedule which apply the weight decay, and it has several hyperparameters, and we're optimizing those. So in this slide, I will provide the details about those hyperparameters as we use them. So in this slide also, I'll be optimizing, I will be discussing the homegrown method, so the manual search we've done or the grid search we've done, our version of the grid search. And for that, I will be discussing the hyperparameter we use. So we have 4 of them. We have the number of epochs, what we call the training epochs. And then we have the number of the warm-up for the number of warm-up epochs. So that's important for the scheduler as it brings the weight up or the base learning rate during that warm-up epoch to its maximum value. And both the training epochs and the warm-up epochs are integers. Now, we have 2 other hyperparameters, the base learning rate and the weight decay. So the base learning rate and the weight decays are both float, and they're constraints, basically any real numbers. But MLPerf put a constraint on the weight decay as shown. So it has to be 0.0001 times 2 to the n and n any integer. So that's the constraint we have for the training epochs and the warm-up epochs. Obviously, they need to be positive integers, the numerals. Now, what we measure is what SigOpt called the metrics or the response. We measure the evaluation accuracy, and this is also a float. So it's a percentage, and or a fraction. You could think about it. And as MLPerf standard, it has to be larger than 0.759 for the resident 50. And when the evaluation reaches that accuracy, we read the epoch number, and that would be what we call the conversion epoch. So how long it took us to reach that efficiency. And obviously, our goal here is to minimize that number. So we would like to have it shorter because that will affect how long we train. The training time is directly correlated with training time. So the manual search is a standard manual search. You start with the known values, and then you do the standard exploration and exploitations. So you will start with a list of values for the training epochs, for the warm-up epochs, and the base learning rate and the weight decays. And you just loop over them. And in each combination, you submit a run to the cluster, and you will get the result back. And the result back will tell you what the accuracy you got and at which epoch, the conversion epochs, and you increment the number. And you evaluate, after you do a bunch of those runs, you evaluate and you adjust the boundaries of these lists and their content. So basically, you adjust the search space, and you keep doing that until you don't get better or shorter conversion epochs. So with that, we're able to lower the conversion epochs by about 28% from the known values. And the computer resources we use, about 85,000 Gaudi hours. Gaudi is our neural network accelerator. And we ran in 2 clusters. We ran on the Kubernetes, and we ran in bare metals. They're basically the same. It's just Kubernetes schedule you run, and bare metals, you have more control over the scheduling. And we thought that's very good. We lowered the runtime by 28%. So we decided to use an optimizer, and we did not know whether SigOpt will give us a better number versus other optimizer or even versus our own manual search, because we thought we lowered it 28%, so we did well. And but we chose SigOpt because it was an API easily integratable with our launcher. So we run on big clusters and we have a lot of launching scripts, and we don't want to deal with any other install on our system. So it was easy just to integrate a few Python lines with our launchers and run. And also, we found out that SigOpt will support parallel evaluation. So that's very important for us to speed up our run. So if we have enough resources, we could run several runs in parallel and get parallel result, and we could speed up the optimization accordingly. And once we started using SigOpt, and every time we get stuck, we got very good customer support turnaround with useful hint and code examples. So got us going fast. So that's why things move. So I just wanted to share those experience with you. So now how we run. So our run and deployment implementations. So if you look at the right-hand side of the slide, you will find that we have a big cluster sit somewhere in the, for us, it's relatively somewhere in the cloud. And we sit at a launcher compute node, and that's the place we launch our script from. So that part is the same what we share with SigOpt runs and the manual run. It's exactly the same. So when we integrated SigOpt, so all what we have, it was nice, it runs in the cloud too. So all what we have to do is just get suggestion from SigOpt. Our launcher will go ahead and pack those suggestions for the parameters. We trying for the run parameter for ResNet and launch the job on the cluster. We read the result back and we relay them back to SigOpt, and we keep going. So that's the cycle of our deployment and measurement. And as for the details about our SigOpt implementation, I will turn to my colleague, Evelyn Ding, to walk you through those details.
Okay, thank you, Basem. Hello, everyone. My name is Evelyn, and I'm a senior machine learning engineer in the Habana Lab. And in the next few slides, I'm going to talk about the details of implementation of the SigOpt. So on this slide, we develop a process flow chart to show the software execution plan from the user perspective. The first, we started the SigOpt from the left-hand side. Then we are going to initialize the SigOpt by defining the few important parameters as below. The first one is the hyperparameter initial boundary. The next one is evaluation matrix threshold. And also the experiment budget. For our implementation, we use about 100 budget for each experiment. The next one is a computation resource, which depends on the availability of number of the accelerator we are planning to use. The last one is a parallel run budget. For example, if we are going to plan to use 64 accelerator, we can define the parallel bandwidth 2. Then we can run 2 sets of the 32 accelerator for the experiment. That's going to help us to speed up the experiment. Then we are going to start the create and configure the experiment. From this point, this is our main execution plan. Our main execution plan has been divided into 2 major loops. The one in the center, dash dot line, that's our inner loop. And the bigger one, the dash line, that's our outer loop. So in the inner loop, which is the user and the SigOpt interface, that's when we run the experiment. We fetch the hyperparameter suggestion from the SigOpt. Then we are going to execute those hyperparameter by training our deep learning model and evaluate if the performance pass the matrices or not. And then we keep going down and turn left. We are going to transfer the matrix back to the SigOpt. And during this process, we can tracking the process from the SigOpt dashboard. And then we reach to the point if we're going to evaluate if we reach to the maximum budget or not. If not, we are going to continue running this loop, keep iterate until we reach to the maximum budget that we define. Then we get out of the inner loop. We started the outer loop. The main purpose of this outer loop is to help to further adjust the boundary to further narrow down the search space to expedite the search process. When we get into this outer loop, the first condition we are going to evaluate if the converge epochs new over the converge epochs old, if the difference is more than 1% or not. If more than 1%, we are going to continue in the outer loop to the next step. We are going to transfer the converge epoch new to become a converge epoch old. Then this is to prepare for the next experiment. Then we are going to continue to the next step, which is by using, we developed our own algorithm by using KMean and supervised machine learning algorithm as evaluator blocks to further adjust the boundary to send to the next experiment. Then the whole outer loop has been iterated for a number of times until we reach to the condition if the new epochs cannot be improved anymore. Then we get out of the outer loop and we save all the data point. And the last good suggestion from SigOpt are going to be ready for us to use. Then we stop the SigOpt. Okay, in this slide and the next slide, I'm going to give some details of how we build up our evaluator block by using the KMean cluster method. On the top left corner, after we run a set of the experiment, then we get all the data point with the hyperparameters and also the matrix. Then we only pick up the data point that meet the accuracy and also pick up the top 75% of the converge epoch data point. Then we are going to split all this good data point of the hyperparameters into the different cluster. Then the baseline of divided into the different cluster is for each cluster, we will keep at least more than 10 observations per cluster. Then we are going to select the best cluster, which is highlighted in the black box on the right-hand side, by using the criteria that to select the minimum runtime mean of that cluster. So we can see from the left bottom chart, that's the box plot. That's a good illustration to show for us to easily to see which cluster has the minimum runtime mean. Then the one highlighted in blue in the box chart, that's the one we select as our best cluster, for example. Then the next slide, we continue build up our evaluator block. On the top left corner, once we select the best cluster, we will use the boundary of this cluster highlighted in the red circle. We are going to translate this red circle, the search space to the right, which is we can see the space between the red bracket. That's our best search space we define from our best cluster. We are going to use this range compared with the SigOpt recommended range. The SigOpt recommended range is highlighted in the light blue between the red and the black bracket. Our black bracket is the widest one, which is our maximum hyperparameter absolute boundary. So we are going to adjust the SigOpt recommended boundary, the light blue range, the boundary between the red and the black. So on the left bottom part, this is the logic how we adjusted the boundary. So it is follow two paths. For example, on the red path, we are going to compare the best cluster upper boundary with the SigOpt upper boundary. If it is close to each other or not. If the difference is less than alpha, which is a hyperparameter we are using, but for example, the 30%, if it is less than 30% difference, we are going to move the upper boundary of the SigOpt boundary towards to the maximum hyperparameter boundary, towards to the right. And the second pass, when we compare the best cluster lower boundary with the SigOpt lower boundary, if it is far away, let's say more than 30%, then we are going to move the lower boundary of the SigOpt towards to the lower boundary of the best cluster. Then we are going to shift the left-hand side towards to the best cluster lower boundary. So this is the way of for us to adjust the SigOpt boundary that we are going to further narrow down the search space to help to expedite the search process. And this is we are going to prepare to send to the next experiment. We would really like this good feature from the SigOpt because this is give the flexibility for the user to define their own optimization method on top of the SigOpt to fit for the different implementation. So I'm going to hand over back the presentation back to Basem, and he is going to give some comparison of the result and provide a few conclusion at the end. Thank you.
Okay, thank you, Evelyn. So here I would like to share some insight about the SigOpt experience and also discuss some of the run results. So I would like to say what we like about the interface, the SigOpt. We like the SigOpt dashboard. We could monitor the experiment as it goes. And also we could monitor the history of the run and the results. Of course, we got all those in some files and log files, but it would be nice to see them all together. And we like the clear visualization metrics with that parallel plot. So you could see the correlation clearly between the parameters and the metrics. So we could see the dependency and how they correlate and how they act with each other. As far as the results, so like Evelyn explained, we ran an experiment with 100 runs, and then we ran another 100 runs. So each run we squeeze the SigOpt, we readjust the SigOpt range, what we tell the SigOpt, the boundary range for those parameters. We adjust it and then we run again. So after two set of experiment, which is a couple hundred runs, we got a improvement compared to the manual search of 2%. And then we ran another round with a 300 runs total now, cumulative. This is cumulative runs. And we got another 6% improvement. And then we ran another 100, and we didn't get any improvement, and we stopped according to the logic Evelyn discussed. So how much computational resources we use? We use about 21,000 Gaudi hours for these runs, and we thought that's very well. Very good for the computation cost as well as the improvement. I mean, 6% on top of the 28% is not bad. So here, I would like to go ahead and compare the two side by side. compare the manual run, or the manual grid run, we did grid search with the SigOpt search. But before I started comparing, I would like to mention that I'm not comparing apple to apple. So when we started with our manual search, grid search, we started from a very wide, we started with known values and very wide parameter space, okay? And we went ahead and we pushed it down as far as we're able to do with that method, with the manual method. Then we started the SigOpt. So by then the parameter space is already tight, and sort of we knew upfront what the good boundaries are and what the good search space is. So we're just challenging SigOpt at that point to find better results, more results. And so the method the method are not the same, or the objective weren't the same. So we started one and we let SigOpt finish. Nevertheless, I would like to go ahead and compare, and because we had some feelings that SigOpt really found us those extra points because it's using Bayesian algorithms, which lock in very quickly on those minimas. And it's a way better than just our manual explorations. And that translated into a 6% reduction on top of already optimized search space. And that's also reduction in epochs, reduction in time. So that's basically goes straight to the bottom line. And also we felt it's a better consumption of resources. So we used 85,000 Gaudi hours versus 21,000 Gaudi hours. Of course, the search was starting from two different points. Nevertheless, we were happy with the resource consumption at that point. So what next? So obviously we provided feedback to SigOpt about our experience. So we already done that, and we continue to talk to them about it. And we looking forward to update our APIs to that's the SigOpt API to the version 8.0. We're still in discussion with SigOpt on that to see which features give us the better, the better, more effective with our implementation and deployment. And also, we would like to evaluate more automated, the automated evaluator on more workloads. Okay, so we tried them on Resonant and BERT, but we'd like to use them on more workloads. And we would like to add correlation analysis of the evaluator for different parameters and metrics. Of course, that comes up when we do the clustering, but we would like to have more explicit analysis on that. And with that, I would like to thank you. And that's the conclusion of this talk.
Thank you.